actual response. If you remember when we started this course, desired response was also the same as the input. So error is basically the difference between the input and the output. Mathematically difference. Yes, that's all what the steady state error is about. So this thing is coming. So if yeah, so there are certain defined values when we talk about steady state errors, which are KP, no, 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 touch the charger, it go off. KV and KA, where K is our K we know as just a constant, and then P position, V velocity, A acceleration. And then from the previous part, realize that position means the unit, sorry, the step input, the ramp input, and the parabolic input. So the KP of a system is mathematically defined as limit as S approaches zero of the function g of S. Please, I may make mistakes also. If you see that I've made a mistake, you alert me. The KV is mathematically defined as this, as S approaches zero of S multiplying g of S, and then Ka is limit as S approaches zero of S squared g of S. Remember, this is for a type 0, so S to the power 0, type 1, S to the power 1, type 2, S to the power 2. And then before we continue, remember that a type 0 system is just a system with forward transfer function. G of S equals, let's say A, where A is any expression you can think of over S to the power 0 multiplying S plus B, S plus C, dot dot dot, where B, C, and the other are constants. For a type 1 is A over S to the power 1 multiplying S plus B, S plus C, dot dot dot. Type 2, A over S to the power 2 multiplying S plus, and so on. So after you find, so yeah, with after the KP, KV, and KA, they help us to find the steady state error. So the steady state error for a type 0 system is 1 over 1 plus Kp, where the 1 is the magnitude. So we are using just U of t. A type 0 system is a unit step, and it is the unit step. So it's 1 here because it's 1 U of t. If it were 3 U of t, to be 3 over 1 plus Kp. If it were 10 U of t, to be 10 over 1 plus Kp. So this is the magnitude of the response we are giving to it. And then you can say denominator is derived from the type of response. For a type 1 system, it's just 1 over Kv. Type 2 system, 1 over Ke. And so if we had maybe 7 R of t, where R of t is a ramp input, that means the answer will be, the steady state will be 7 over kV. That is what it means, not every time 1. It depends on the value we are given. So I would like us to, I don't know, do some, yeah. So let's take this question and try to solve for it. So you know that U of t is in step, this is ramp, this is parabolic. So they said for the unity feedback system shown here, where this find the steady state errors for the following test inputs. So first and foremost, when you just look at this, you realize that it is a type 1 system. And then, oh yeah, I forgot to mention this in there. So for a type 0 system, so How do I write it? Ram is this times 0. Okay, yeah, so step ram parabolic. Parabolic. Is I'm sorry if the is basa basa. It's not my fault. For a type 1 system, for a type 2 system. So for these are the steady state errors for different systems and type of input. For a step input, it will have a finite. By finite you mean we will have a number, not so we can either have zero, a finite number which is a number from negative to positive, and then we have infinity. These are the types of errors we can get. So we can get no error, we can get a certain error we can work on, and then we can get an error that is very big that we can't work on that error. So basically the effect of learning this is, you see, the control system thing as a whole is basically modeling physical systems, and then maybe you've created a physical system, then you are now testing to see, so this is the error associated with it, let me try to change, let me try. So yeah, if you have zero error, that's what you want. The finite error, it can be worked on, but then infinity error basically means change the whole thing down, sort of. So for a type 0 system, the step response gives it a finite error. The ramp and parabolic response, infinity. For a type 1 system, the step response gives it a zero error. It will give you a zero error because it is not a, that input cannot even cause anything to it, sort of. The ramp will give you a finite, and then the parabolic will give you infinity. For a type 2, zero, zero, finite. So you can realize that, and then if you take it as if ramp is greater than step, sorry, take it as if ramp is greater than step, parabolic is greater than ramp. So for type 0, finite, infinity, infinity. So like you can basically move from 0 to finite to infinity. So if it is your type of system, I mean relating to the input, you get a finite error. If you are greater than the type of system, you give it an infinity. If you are less than, you give it 0. You can think of it that way. If it does not make sense, forget about it. So yeah, the question. So yeah, you can see that this is a type 1 system, so it will work for this. But then the fact that it will work for the ramp error does not mean that it will necessarily not work for this. And then the question says find it, so we will find it. So first and foremost, we'll find our KP, KV, and KA. First KP. KP is just limit as S approaches 0 of the whole system. So when S approaches 0 here, 0, that means everything will go to 0, every s will go to 0, and then we'll be left with 450 times something over 0 times something, which will give you a number over 0, and we know that to be infinity. So our kp is infinity. For kv, it is limit as the s approaches 0 of s times j of s. So before you do it, you multiply this by s. So s will take care of this s, and now you put 0 at where s is. So then we have 450. Please don't understand the mathematics, you can stop me, we'll explain it. Don't be shy. If you are shy, you would have wasted your time and your data. 450 times 8 times 12 times 15 all over 38 by 28. I don't have a calculator, so I may give you wrong values, but what matters is that we know what we are doing. All over here 3, 4 over here 7. If you have a calculator, you can punch it and give me the value. 2 here 40 here 90.
Godwin,
Yeah, I was
please can you go back to after the table the table thing, the finite, infinity, infinity, yeah,
this.
after this thing.
Uh-huh.
So
I should
like
go to
start
after
solve
this.
yeah, so start solving the question again, like what you wrote at the
Oh,
beginning.
okay, okay. So for her sake, let's go back and start. So this is the question. They said for unity feedback system, this. Find the steady state errors for the following test inputs: 25 u of t, 3070 u of t, 4070 squared u of t. This is a step input, this is a ramp input, this is a parabolic. And then they've given us the system, they've drawn it for us. But even if they are not drawn it, they say for the unity feedback system with so oh yeah, if it wasn't drawn, they would have said that is the forward transfer path. So we've been given
Okay.
this, and we are finding the steady state errors for all of them. To find the steady state
Okay.
errors, you need Kp, Kv, and Ka. If we were not, let's say we were not given this, and we're only given these two inputs, there will be no need to find Kp. But then here we were given both, we're given all three types of inputs, and that's why we find Kp, Ka, and K whatever. So yeah, now going to the finding of Kp and the rest. Kp is limits as s approaches zero of the g of s, and then this is our g of s. So we'll find the limit as s approaches zero. Basically, it just means wherever you see s, put zero there. So we will have
Okay.
450 times 8 times 12 times 15 all over 0 times 38 by 28. And then this will give us a number over 0, which equals infinity. This is not a steady state, or this is just the KP we found. The table I drew at this side, they were for the steady state errors. We'll find the steady
Okay.
state errors later, but before you find the steady state errors, you need the KP, KVN, unless you want to use the long way, but then for uniformity sake, let's all stick with this. If you know the other one is good for you. So now we found our KP to be infinity. Now let's go to finding the KA. KV, sorry, yeah. Let's go to finding the KV. For KV, the formula is limit as s approaches zero of s multiplying g of s. So this is our transfer function g of s. So before we start, multiply it by s. Then multiply this by s, this s will cancel this s down here. And after that, we'll do the limit part. Wherever we see s, we'll give it a zero. So therefore, our equation will now look like this, because the s here has been cancelled by the s that we multiply with. So now this is our equation. So this was where we reached. Vanessa, please, are you
Mhm.
fine?
Yes, I get it. Thank
Okay,
you.
don't worry. So yeah, we'll get, with this thing we'll get something around 609. There are decimals, but for, let's just leave it at 609. So that means our kv is 609. I've approximated, it's not the actual value, but what matters is we understand. Then the last part, we need to find the ke. The ke is limit as s approaches zero of s squared times g of s. So you multiply this by s squared first, the whole system by s squared first. So if you multiply, that means that s will take care of this s, and then we'll be left with this multiplying s over 38 multiplying 28. So if we take all the s's to zero, this will be zero, and then what we get to be zero over a number, which will give us zero. So that means the k a will be zero. So we've gotten our kp, kv, and k. I hope everyone is fine till this place. Remember that the kp and whatever are not our steady state errors. They are just things that will help us find the steady state error. They are not the actual steady state error we are supposed to find. So then, now let's find the errors. For the steady state error for this input 25 u of t, oh, it's not writing. Uh, Okay. So for 25 u of t, the error is 25 over 1 plus kp. It's 25 because the magnitude there is 25. In the slides, we see 1 over 1 plus kp because we are always using a unit step response, so it's 1. But if the magnitude there is 25, that means here is 25. And then we'll get 25 over 1 plus infinity, which is the same as 25 over infinity. And then that will give us 0. So that means the steady state error for this is 0. For 25 u of t is 0. Then the next one is 37 t u of t. So that would be the 37 over kV. So 37 over 609, which will give us a certain number. And then we'll get around 0.0607. Then the other one would be 47 over Ka. That would be 47 over 0, which give us infinity. So if you realize it, we had a type 1 system from the question and a type 1 system from the other table. We know that it will be 0 for step response, a finite number for ramp response, and infinity for the other one. So we had 0 for step, a finite number, and infinity. That's all. If this thing came in exam and did not want to waste your time, you just realize that it's a type 1 system. So you just write it straight away that 25 u of t will give us 0 because it's a step input for type 1. 47 t squared u of t will be infinity because this. Then you now solve for the 37 u of t to save your time. I hope everyone is okay with this. Please, if you have a question with this, unmute and tell me. If no one speaks in 10 seconds, I assume you understand. I'll move on.
Godwin.
Yes,
God. Yes. You said that if it comes in exams and something something, I didn't hear the something something.
I said so. In case say this question is in exam, because of time, and then you know that this system is a type 1 system. So from your knowledge, you know that a type 1 system will the step inputs will have an error of 0, and the parabolic inputs will have an error of infinity. So you can just write those one down first before you go and solve. It's better than solving all three in your exam, since you already know what this and this will end up giving you.
Okay.
Is
Thank
that
you.
you're right?
Yeah.
Okay, so you're moving on. Yeah, so for a unity feedback system shown here, we did not show the figure. Then they said, what is the expected percent over? Let's forget about this for now. And the second one as well. Right, well, you will, if you know it, you will know it. So what's the expected percent overshoot for unit step input? Okay, let's just try to solve it. So they've given us JS, and then it's a unit. If we are just giving that it's unity feedback, it's always good to assume that it's a negative feedback system, not positive. So the actual transfer function T of S will be 5. Instead of 5,000, let me just do it 50 because of time. S squared plus 75s plus 50. This will be the whole transfer function. Now the first question says percent overshoot. You know that percent overshoot formula is e raised the power negative ish. I'm hot too. I think damping ratio pi over square root of 1 plus damping ratio squared. So through, and then we already know how we find the damping ratio from this thing. So you find your damping ratio from here, you put it here, you find your percent overshoot. The settling time is just 4 over this, where is 4 over this. And then so even this one is, so you know that this part, the 75 equals 2 damping ratio omega n. So that means damping ratio omega n is 75 over 2. And then you just come and fix this in here. So here will be 4 divided by 75 over 2, which will be 8 over 75. That's the damping the settling time part here. Then the percentage overshoot, it will be plenty, so I can't solve. I don't have calculator near me, sorry. But then this not why we are here. We are doing the error part. So, but then I hope everyone understands how this will be done. So yeah, find a steady state error for an input of 5 u of t, 5 t of t, 5 t squared u of t. So you can realize that this is also a type 1 system. So straight away, we know that this will give us 0, this will give us infinity. If you doubt, then you solve. Then the next one says you find for 5t u of t. So that means that we'll find our kv. Kv is limit as s goes to 0 of this expression. So s times 5,000 over s multiplying 75 plus s. So this will take care of this. Then this s will go to 0. So we left 5,000 over 70. Let's take it as if it's just 50y. I don't have calculator. So 50 over 75. And then 50 over 75 will give us 2 over 3. So that means that our kv will be 2 over 3. But then it's not kv we need, it's the error. And the error is 1 over kv, which is 1 over 2 over 3. Hey, sorry, not 1. Here is 5. So it will be 5 over kv. So 5 over 2 over 3, which will give us 15 over 2 equals 7.5 units. Since we are not given any units, it's good to just write units there, because sometimes the error will be in a voltage, a current, or any other system. Please, are we all okay with this? Okay, so I am assuming we are all okay. Now, let's look on- so yeah, so now we've been dealing with unity feedback systems. But then what if we don't have a unit? And then before we continue, I forgot something. We can only find the steady state errors for stable systems. So normally, if you are given an unstable system and you are told to find the error, there will be no error because the system is unstable. And then maybe some of those questions he has, then later he will laugh at you as his new student. But then the book gave an assumption that let's take every system to be stable. That's what I'm also taking. But then, in actual sense, we are always supposed to find whether a system is stable before we find the errors. But then, yeah, let's assume all the systems are stable again. But in actual sense, that's what you're supposed to do. I don't know whether you have to do that in exams or you just go with the assumption. But whatever it is. eh. So yeah, we've been dealing with unity feedback systems ever since we started. But then what if we have a non-unity feedback system? Or wait, before that, what if we have a positive feedback system? So all along is the negative feedback. So for a positive feedback system, instead of your work to be just j of s, then negative, what if it's actually positive? So if it's positive, you can just put a negative one. And I to change everything. Yeah, okay, to go back to the non-unity. Yeah, so let's just focus on the non-unity for now. Later, you see. So for non-unity feedback system, so for dealing with non-unity feedback system, you must first change the system to a unity feedback system. And how is it done? Remember that a unity feedback system looks like this. Looks like this, where this is g of s. But then a non-unity feedback system will now look like this. No unity gain, then J of S. So we can change, and then remember that this is a feedback system. Yes. So we can just change this to a feedback system, a unity feedback system, by paralleling the non-unity feedback system with a unity gain, in the sense that, let's say this is X, we can just make here X minus 1 and then parallel it with a 1, and then they will all come here this way. Now why am I saying this is the same as we had a system, and then you know that for parallel systems we add the gain, so we'll add gain 1 to gain 2, and now we had a system that looked like this, where here is X, no unity, and now I'm saying let's parallel it with, let's change it to X minus 1, and then let's parallel it something that's 1. When you simplify this, please, you get X minus 1 plus 1, which you change to 1. So in block diagram simplification, this will change back to this. So that means we've not done any new thing to it. All we've done is that we have changed it from a non-unity feedback system to a unity feedback system. Now, when we change it this way, please, as if you don't understand anything, you stop me. If you change to this way, then we just take this as our feed, as like we just simplify this. So I'm coming, let me redraw everything again, so that, let me redraw it slowly, like, yeah, so that it'll be better. So we start, so in a, we've been given a function, a block diagram like this. X meaning is non-unity. So what we will do is we change it to any feedback system first by paralleling it with a gain of 1, and then when parallel we'll make it X minus 1, and then we'll parallel it with a gain of 1 means it's just the line going. So now we have this, and then when we do this, we will now change this to a system looking like this. Now let me call here B of S, and then this, where this B of S is the feedback. Let's take, sorry, where this B of S is the feedback of J of S and X minus 1, and you know what to do with a feedback of J of, like it will be J of S over 1 plus J of S multiplying X minus 1. So this is what it will be. I hope everyone gets it. As I said, don't get, unmute and tell me. So this is what it will become. Then it becomes this, if we are making this look like any feedback system, that means our B of S will now be equal to J of S over 1 plus J of S H of S. Yeah, so instead of X, H of S is how we normally do it. 1 plus J of S H of S minus J of S. How did we get this? It's just the J of S multiplying H of S minus 1. That is this place. This place. J of S multiplying X minus 1. So we are just expanding the bracket. So J of S H of S is this. Then J of S times negative 1 is this. That's where that is gained from. So you just do this, and now you do your, so now this will become what you'll be using to find your KP, KV, and K. I hope you all get it. Now, there is something you have to know about this, in the sense that when you have a B of S, so for the purpose of us here, is that's what they use. I don't know why I say B. So when I say B of S, it means that JH minus J. For the B of S, do not make the mistake of using the denominator to just find whether it is type 0, type 1, or type 2. It's hardly works that way. We'll solve a question then you look at it, but then I'm just making you aware. So this is how to change from type 0 to sorry, a non-unity to a unity feedback system. Please, is there any question pertaining to that?
No, please.
Mhm. Your space. Thank you. Okay, so there was this question in the slides. Let me look for it and add it to this slide. Please give me a couple of minutes. Um, so is your able to see the question or it's too small? No, it's too big. Anyways, so we've been given a system and then a non-unity feedback system to find the value of k to yield a 0.1% error in the steady state. So here they've given the steady state error and then you find k. Them giving you k means that the system is not a unity feedback system. It is either an expression or a constant. Many a times you get a constant. Yes, if you are the one supposed to find, many a times it will be a constant. But other times you can be given an expression there. So the first question, we are supposed to find a system type. The second, we are supposed to find the error. And so as I was saying, you cannot just look at this and say because S squared is here, it is a type 2 system. You'll be wrong. You may be wrong. Sometimes it will work. You may be wrong. Sorry. So first and foremost, let's find our B of S from this. There's no need to go and prove the whole thing. So your B of S will now be S plus 1 over 1 plus K S plus 1 over S squared S plus 2 minus S plus 1 over S squared S plus 2. Hey, sorry, the G of S will so this divided by S squared S plus 2. So this is it. Then we'll do the simplification. When you simplify this, you get 1 plus, I'm just doing with the denominator. So 1 plus k minus 1 multiplying s plus 1 over s squared s plus 2. S plus 2 come here. If I multiply this, which will be k minus 1 s plus 1 plus s squared s plus 2 all over the denominator. So that means that our b of s will be, is if I make a mistake, let me s plus 1 over, i'm I'm expanding this straight away, so we get sk minus s plus k minus 1 plus s cube plus 2s squared. This is what we will get as our b of s. Now this is what we use to find the expressions and the system type. I hope everyone gets it. If you don't get something, just unmute. If you don't raise your hand. Now we want to find the system type and the key. So you realize that when we are finding K, P, K, V, and K, A, if it is a type 0 system, we get a finite value for Kp. These are not the steady state errors per se. I'm talking about Kp, Kv, and Ke. If it's a type 0 system, we get a finite value for Kp. and then the rest will be either 0 or infinity. If it's a type 1 system, you get finite for KV, type 2 you get finite for KE, and the rest will be either 0 or infinity. So that's how you find your system type here. You can't just look at it straight. Maybe in the book talks about some integrations and things, but I feel it's a longer way to get to it. But if that one will be easier for you, after class you can text me or you can look for it on YouTube or internet, however. So first you will have to find our KP, KV, KA to see the one that will give us as finite value to get our system time. So KP is limit as s approaches 0 of g of s. So now this is our g of s, which is basically b of s. So when you put 0 inside, it seems we get a finite value. Here we get 1 over 0 k minus, yeah, so we get 1 over k minus 1. That would be, and so that means the system is type 0, because we've got, and once you get the finite value for one, the rest won't be. But then just to show, so kv will be limit as s approaches 0 of s times j or b of s. So you multiply all this by s. It can't cancel anything down here since you've not factorized this. Don't go and cancel it. It can't cancel. So when it multiplies, when everything goes to 0, here will all be 0. It will be the same for limit as s approaches 0 of s squared j of s. So it will also be 0. That means that our system has a finite KP. It is a type 0 system. So for non-unity feedback system, don't make the mistake to go and look at this to solve, to just write that because it's to the power 2 here, it is a type 1 system, it is a type 2 system. That's very wrong. Now we have found our KP and we have found our system type. So now we need the value of K to do whatever we have to. So the question says that for what value of K will the system be, whatever it is. So then,
Godwin,
yeah, I was,
please, with finding the type, when you get a
mhm.
finite value, that's the type, or is there any other way to find it?
There are other ways. The book talks about integrations, which you can use it, but then I feel it's a longer and stressor way. Is stressor correct English? But like, I feel like it's more stress to do that. So this is what is very easy for me. But then the other way, so you can look for it and then do it. But you, for me, my point is you can't just look at the function here and determine. That would be wrong. That's what I'm trying to put across.
Okay, okay, all right.
Yeah. So now we have to find our error. And since it's a type 0 system, that means the error will be only like 1 over 1 plus kp error. So 1 over 1 plus kp. Now, yeah, we're also not really giving the type of input. So we will take it as if it is a unit input. That means we will take it as if it's just, sorry, we will take it as if it's just one u of t. Because if it were another u of t, that means here won't be 1. Yeah, so we just take as if it's 1 u of t. So it will be 1 over 1 plus kp equals 0.001. Yeah, because they gave to us in percentage. I'm not really sure whether we are supposed to write just 0.1 or change it to decimal, but just to be safe, let's do this. So that means that 1 plus kp is equal to 1000. Sorry, 1000. 1, 2, 3. Yeah, so one, we just brought this here. We brought this down here. So this equals this. That means that kp equals 999. But then it's not k. So we found the expression for kp here. So 1 over 1 over k minus 1 is equal to 999. So that means that k minus 1 equals 1 over 999, which I don't know what it is. And then k will be equal to 1 plus 1 over 999. So this is the value of k that will give us a 0.1% error in steady state. I may be wrong actually, but then please, is there any question or any addition or any subtraction? Okay, so it seems there is no. So yeah, my point is if you are given a non-unity a. Yeah, please, yeah. Jude, please, yeah, you can speak.
Given the feedback system, what if you have multiple feedbacks? Are you just going to parallel all of them and introduce a negative one?
Yes, please. So if I'm getting correct, let's say instead of just K, we had another feedback here. Let's make it A. It's actually an expression, but just let's make it A. And then you have another one B. Is that what you're asking for, Jude?
Yes.
That we have. Okay, yeah. So you will have to parallel it as A plus B, and then combine them as one system. It's because if not that, you have to find the unit. You have to find the feedback for first, second, and third, which will be very long. So you just parallel it into one feedback system, and then start solving on it. Is there any other question?
Let's the last one. So how are you going to get
Okay.
the final expression?
Okay. So if I'm getting you correctly, I'm coming. So if I'm getting you correctly, so let's just say the g of s is there, and then let's say we have a feedback a of s. Okay, no, let me just so s plus one, another one 3 over 2s minus 2, and another one 5 over s squared. So if all are negative, if all negative negative, like when they all enter the this one, you see negatives by them. You if you don't, if one is positive, if one is positive here, just make the inside here negative. And so let's say in the question this negative is not there, here is positive. You make here negative 5 over s squared and make here negative, so that the negative and negative will make it positive. But then let's say it's not there, so now we have this. So you parallel this, this and this, and then in parallel s plus 1 plus 3 over 2s minus 2 plus 5 over s squared. Let me just make it so that the thing will be easier. So the whole thing now will become okay, you s plus 1, forgive me. So the whole thing now become s plus 1 multiplying s squared multiplying. Nah, it won't be that. It will be a whole lot of mathematics. Sorry, let's do it. Let's forgive me. So we have, so then the one goes. So let's make it just s so that it will be easier. So then we have 3s squared plus 5 multiplying 2s minus 2 all over s squared 2s minus 2 plus this is equals the addition of these fractions plus s. So that means the whole feedback system will be s cube multiplying 2s minus 2 plus 3s squared plus 5 multiplying 2s minus 2 all over s squared 2s minus 2. So then now our feedback, our whole work will look something like, so now our whole work will look like this. Instead of what we have here, it will now become j of s in a feedback with this whole thing. So like this whole thing will now be in this, and now that will be your h in the j of s h of s minus j of s one formula here. Jude, please, you get it.
Yes.
Yeah, so you just add them and then it become one feedback system. This is another question.
Yeah, and a last question. You see, for the first one you wrote, there was like a shorter formula. You just wrote g of s over 1 plus g of s h of s minus g of s.
Yeah, yeah.
Is there
That's
any
if you have
shorter
a
formula for this?
unity. No, that's the actual shorter formula. It's not, it's okay, it's not shorter formula in that sense. It's just that they have just simplified the feedback into this for you so that you just write this without going through the stress of changing from non-unity to unity. But then that's all you have to do. So if you have a non-unity feedback system like this, where h of s equals k, yeah, where h of s equals k, you just change this into this. That's what they mean. And then you work on it as a unity feedback system. Please, you get me.
Yeah, thank you.
Okay, you're welcome. Please, is there any other question? Okay. So this question is very long. Should we do it? We're all tired, right? So let's move on. Okay. But anyway, so the question says the question says find the closed loop transfer function. Then we know we did this last time. You do this. Then now this and this will be in cascade, and then it will be in feedback. It will be in unity feedback with all this. So after you find this, that will help you. Okay, so let's just solve it. So this and this are in unity feedback system. So we have, hey, sorry, this and this is a feedback system. Forgive me. So it will be 1 over s squared s plus 1 over, please, we are not finding the feedback system for this one, we're actually doing the transfer function. So over 1 plus 1 over s multiplying 1 over s squared s plus 1. So this thing will give us s cube s, and I may be wrong, plus 1 here. So that side will be 1 over, like this side when simplify, you get 1 over s cube s plus 1 plus 1. Then you can multiply it with this since it's in a cascade. So it will be times 1 over s squared s plus 3. When you multiply this, you get s to the power 5 s plus 1 s plus 3 plus, please, I'm coming. So when you do this, you get 1 find the KP, KV, and KA before you will do this. So it will be a type well, I don't even know what it will be, but then if you solve them, that's where you can determine whether it will be a type 1, a type 0, a type 1, or type 2. But then we are skipping it since we are all cool with it. Another question about unity feedback. So yeah, you bring this one here in the 1 plus J H minus J formula. Then and they say find the appropriate static error constant. So it means is it either Kp, Kv, or Ke? So you find Kp, you find Kv, you find Ke. The one that will give you a finite value is it's what it is. So then they say what is the value. So yeah, so first when you find then, so the static error constant to be either a position static constant, a velocity, or a this. After that, then the next part you write the value of what you got. Then now what's the steady state error for units? So even if it was in an exam, because they have given you that what is it for a unit step input, you know that it is a type 0 system because of this. Actually, the man can trick you and then it will be infinity. But then me, I'm thinking is that so times 0. So yeah, you can look for the question and then you solve it. All the questions are from the textbook. Someone just puts questions on the slide for me, so not bad. But if you want after that, I'll take a picture of everything and send it. Hey, end of slide. Hey, it's almost the time 4:35. Okay, so then after this, then let's do please, is there any question with the steady state error thing? Is there any question with steady state error? Any question at all? Like any question at all about steady state error or stability or the reaction of since last week we did reaction and the stability. And so I'm thinking as if we did all the three in one. Any question about these three topics? Stability, steady state error, and reduction of diagrams. Hi. Please, if there's no question, someone should unmute and say there is no question. For me to know I'm
There's
going to
no
put it
question.
There is no question.
super sharp. So then let's move to root locus. As you can see, there are no like the slides end here. So like the person forgot what the root locus. So like hey, we'll just be I'll try to I don't know from my head, which is very bad. And then let's hope God will help us. So root locus is yeah, yeah, yeah. Yeah, so please, root locus is a graph, and then the graph gives you the different on the interpretation of the root locus is the different behaviors of your control system at different values of k, where k is the gain of your system. So at different values of the gain, root locus gives you the different behaviors of the system. Yes. Then so in root locus there are rules, and then that is please I don't really remember them. Okay, so I'm coming. This the root locus part to be very slow. I'll try to be looking at the slides to do it. So I'm sorry if from here we're going to be slow for you. Okay, so then in the we have 1 plus that in kg of s h of s equals 0, and then this is our open loop transfer function K is just a constant. This is the function. Normally, we would have taken an open loop transfer function as G of S, but then here they say take it as all of G of S, H of S. This does not mean that when maybe we are given a transfer, a block diagram like this, just go and multiply this and put it here. That would be wrong. It's just that after you solve the thing and then you get this, and then say you get, no, this is a unity feedback gain. We are taking this whole thing as the kjh. It's not that you just go and multiply this j of s by h of s. That will make your whole work wrong. So yeah, this is the open loop part, and then this the, and then the whole thing is the closed loop transfer function. And then we also have, see, you look, let's just solve question. I don't remember the rules, but then as we are solving, the rules will be coming to us. Please, I hope everyone will be okay with that.
Yes, please.
Yeah, thank you. So let's say we are plotting the rules locus for a certain system, and then maybe we have the function to be s minus 3, s plus 4, then s minus 1, s minus, sorry, s plus 1, s plus 2, s plus 3. Yeah, let's say we have this. Oh. So the things you have to take note of are the zeros and the poles. So the zeros of this are 3 and -4, and the poles are 0, -1, -2, -3. So the result is just a graph, and every graph you need your x and y axis. But then in here it is our this sigma and JW axis. And then sigma is just this damping ratio omega n. Then this is just j omega n. This is it. So if you're actually given the expanded here, you know where to put them. So we have our zeros at 3 will be somewhere here, -1, -2, -3, -4, and then -4 is here. So we have our zeros here, and then we have our poles at 0, -1, -2, -3. Now we know that we have two graphs that will go to infinity because we have four poles, two zeros. So that means there will be two lines going to infinity. Then that's when you have to go and find those things, those formula. But if you think about it, if we have two lines going to infinity and then the thing must be symmetrical, that means one is going up, one is going down. So this one will help you that I'm now going to use the formula and then going to find the angles. If you don't know what I mean, let's just find the angles. So yeah. So the formula is sum of the poles minus sum of the zeros over pole number minus zero number. So sum of the poles is -1, -2, -3. That's -6. Then sum of zeros is -1. Eh. Okay, so a -1. So it will be -6 plus 1 over 2 because 4 minus 2. So we have -5 over 2, so -2.5. That means our centroid is this -2 is somewhere here. This is our centroid. And then I go to the angle part, that is 2k plus 1, if I am right, times 180 over the difference here. Instead of writing this, you can just put your mind as is the difference. So over 2. So this will give us 90. So this will have two things. So at k equals 0. We start counting from 0. The first centroid will be at, like the first line will be at 90 degrees. Then the next one at 1, it will be 270 degrees. That's it. So it's at this centroid, we have, let me use black ink. This 90 degrees. Remember, we are taking the angle from here. And then this 270 degrees. The answer is another responsibility. And then before that, okay, so now if you are looking for a root locus, at the left of every odd number of pole, this one, there is a root locus. So at the left of here, there are 0 things. So there can't be any root locus here. Now there's 1 here. So we'll draw a root locus here. Then between this and this, there can't be a root locus. Between this and this, there is a root locus. Between this and this, there can't be. Between this and this, there is a root locus. Then now we will show the arrow. The root locus always move from the pole to the 0. That is for a negative feedback. For a positive feedback, the things change, but then in class we've always been learning negative. So it goes this way, it goes this way. And then now we are left with this. Wait to ah, ah. Please, I'm coming. Actually, please, I'm writing. Can you see? Hey, please, can I be heard? Please, can you see that I'm doodling some things like some S or it? Okay, thank you. So then, so where were we? So now we know that from here to the root locus will come this way. That means that they have to go out. And then is, so now here is the problem. Actually, I don't know how to draw it, but then you kind of make it go near the asymptote and then draw it upwards. This I'm not sure, to be honest, I'm not sure. But then he said we are not supposed to make it sharp lines. That's why I've bent it this way. I think any sketch you do, he will give you correct. Once it kind of follows the rules, I think any sketch you do, he will give you correct. But then to get the actual rules, because you need MATLAB or any other coding platform. So this was the rules locus to be like. And maybe we have to find a breakaway point, as in where exactly these rules locus start to go up. So the man gave us, he said we can just use 1 over, oh, this thing. Please, can you hear me? Please, can you hear me?
Yes.
Please, can you hear me? Hello. Oh, okay, okay, thank you. But then my laptop is, I'm coming. 2 minutes. Oh, I pressed on key. I pressed on key. It's my fault. Oh. Okay, so hmm, let me back. Eh, Please, I'm coming. Give me a couple of minutes. Uh-huh. So S minus 3s plus. Yeah, so to find the breakaway point, you will, with the equation we were given, you either find the differential of, so let's, if this is the numerator and this is the denominator of your expression, this, please, I'm not using any ng dg, please, those things confuse me, so the intelligent ones will learn that. But then to find the breakaway point, you can either find the differential of where this small, okay, so let me change this to capital N and small capital N. So you find the differential of negative denominator over numerator to find the breakaway point, then you're going to zero. So the values of, and then yeah, we change the s to sigma. You can, if you want, you can just use s as it is. It does not change anything. What matters are the values we want. So you equate this zero, and the values of sigma are the breakaway, and they are breakaway and breaking point. So let's try to solve this. Or you can use 1 over s plus 3 plus 1 over. So let's try to solve this. So the, if we expand the whole denominator, we will get s squared plus s multiplying s squared plus 5s plus 3, sorry, 5s plus 6, which give us s to the power 4 plus 5 plus 1 is 6s cubed, 6 plus 5 is 11 s squared plus 6 all over s squared plus s minus 12. So yeah, if we are finding the breakaway and break in points. So we'll find the differential of this, and then doing the difference, this is a quotient. So you differentiate the top part. That'll give you 4s cubed plus 18s squared plus 22s plus 6. And then the down part will give us 2s plus 1. And by quotient rule, you multiply a split. You multiply this by this, then this minus this plus this by this, all over this squared. This is plenty, so let's, so in case maybe our sigma, we get say 2 or 3 values of sigma, so maybe we get negative, the two was between, I mean, negative or negative 2. So maybe we get negative 1.543, negative 2 point, no, sorry, negative 7.84. So let's say if we had gotten negative 1.543, negative 7.84 after we solve this, let's just say we got that. You realize that we have, this thing just helps us find both the breakaway and the breaking point. If you want to know which one is breaking and which one is breakaway, you find the minimum and maximum values. Use one of them as, one of them will be minimum, one of them will be maximum. So now you have to then differentiate your expression again, which is long. So you can just look at your graph. These are negative 1, these are negative 2. So one of the points was between these. One of the points was between negative 1 and negative 2. That was negative 5, negative 1.543. That means that our breakaway point, as it is going away, is negative 1.543. And then obviously the one left will be the break-in point. Please hope you get what I'm trying to say. So like, instead of you solving them again to find the minimum and maximum points, after you sketch your, and then in exams you have to sketch, unless he chooses to give us graph books to draw it, but then we will by all means sketch. So if you sketch, you will know that at least my breakaway point is within this range, it's within this range. So per your values, you choose, you write that breakaway point equals this, breaking point equals this. Please, you get what I'm trying to say? Please, you get what I'm trying to say? Hey, please, can I be heard? Hello. Hey, wow. Please, can I be heard? Ah, okay, okay, I can see that. Thumbs up thing. Yeah, so that's how I find a break-in and breakaway point. And then I think there's a third one, the angle of something, which we also have to look at. Yes, Vanessa. Vanessa, please, you can speak. Okay. Please, I'm coming. Give me a couple of minutes. Okay, so let's say we've been um uh-uh. So let's say we're given this to sketch the root locus. You when you are sketching, you just do away with the key and then do the rest. You do like you not factor in the key. So the poles are the zero is -3. The poles are negative are 0, -1, -2, and -4. So say we are sketching this. Please I'll be sketching through it. Permit me 0, -1, -2, -3, -4, and then yeah, that's all. So pole, 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 and 0, then there's another pole. Then we are supposed to sketch the root locus. So between this and this, there'll be a root locus. I don't want to explain that. Between this and then this goes. And then from the number of poles and A, we know that three root locuses will be going to infinity. So then this and this, they will go out. This goes towards this, and then this goes here. So first, we will find the centroids. So sum of poles are -7. Sum of A is -3 over 3. So we have -4 over 3. That will be somewhere here. -3 is somewhere here. And then angles will be 2k plus 1 times 60. 60 because 180 over 3. 3 this 3. So we have 60 um 180 300. So the asymptote will be 60, 180 is this, and then 300. Then we'll have to sketch. So that means that this goes up somewhere here, it goes up somewhere, and then this is already on it. Like this is the 180 line, and this already on it. So we pray. So this is the root locus sketch. So you show the arrows this way. Now the next thing, let's find the break away and breaking point. Let's if it's long to we'll just assume any number for it. So we have negative of s into bracket. Let me see. I'm coming. S squared plus 2 3s plus 2, and then there's s squared plus 4s. So s the power of 4 plus 7s cubed plus 12 plus 2, 14 s squared plus 8s. So we have negative of s to the power 4 plus 7s cubed plus 14s squared plus 8s all over the numerator s plus. Remember that when we are dealing with the root of course, we kind of do away with the key. That's why I've shaded it out. So then we have this. Then we'll differentiate. So when differentiate top part, we get negative. Remember the negative multiplies also negative 4s cubed minus 21s squared minus 18s minus 8, and then the down will be 1. So when you multiply this like this, you get another plenty thing. The thing is so long. Why? Real. Oh, oh, oh. So then we'll have negative 4s to the power 4 minus 12 plus 21 is 33s cubed minus 18 and 63. Wow. 81. That's if I write s squared minus 8 54 62 s minus 24 all plus, because it's all minus 1 multiplying negative of this. So negative negative will become plus. So all plus this whole thing again. So because of time, I'm not writing this, but then okay, let me just write plus s to the power 4 plus 7s cubed plus 14s squared plus 8s. Then we'll do the mathematics. So we get negative, and then the denominator is this squared. But then the denominator will go to 0, so there's actually no need to stress yourself over it. So negative 3 is the power 4 minus 28, no, 26 is the power 3 minus 67x squared minus 54s minus 24. Then equate all this to 0. Then find the values of s. Values of s. Now you realize that this one will give you 4 different values of s, but then we just have 2 going away. So obviously the one only one of them will be in the range of 0 to 2. Yeah, but then calculator 2 will be very plenty. But then yeah, only one will give you in the range of 0 to negative 1. So that point will be your breakaway point. And then for the breaking point, as you can see, it's going somewhere here. So you just try to find if there's one positive inside, that will be the breaking point. If there are two positives, the breaking point will be between, it will be one of those two. But then that's what I'm just trying to say. So it comes here, it comes here. Now there is also knowing where this line cuts the axis, like where it cuts the j axis. For that, you will have to yes, Celoid.
Please, I can't see your screen.
You can't see my
Yeah,
screen.
what you are sharing with us.
Hello, I can't hear you.
Yeah, I can't see your screen. What you are presenting to us.
Oh, sorry. Hey, so every the mathematics I was doing, you were not seeing.
No, please. Or just
So
hearing.
like right now on my
No,
screen there is.
it's blank. I'm just seeing Kwabena is presenting, but I can't see what you are writing on the screen.
Oh, sorry. Please, is he the only one, or please is
Yes,
someone else written there?
he's the
So
only one.
so you can see Kofi,
Scroll
you
up,
can
scroll
see.
up. Yeah, I can see.
Fred, please, can you see?
Yes, I can see. Lloyd, scroll up.
Lord, please,
See
I
it.
think you have to refresh or something.
All right, I'll work on it from my side. Thank you.
Okay. Yeah. So then, so there's also finding where the line cuts the JW axis. Now, if you take note, the JW axis, like when we were learning stability, we said when something comes to the right half of the plane, it becomes unstable. So finding the values, so finding where this thing has the JW axis, you are basically finding the values of stability of this, like of the graph. And then for that one, you have to actually find the whole transfer function and then do a Routh-Hurwitz criterion. The values of k that you get, you yeah, you find the omega values that correspond to that. Yeah, please, you time is fast spent, and then I did not prepare slides for this, so can we postpone it to say Monday or Sunday for only the locus?
Yes.
Okay.
Please, I hope we are all okay with that. Raw.
Yes, yes, you're okay.
Yeah, okay. So thank Joe for joining. I mean, welcome for joining. And if there's any question, please you can ask before we finally end the class. If you are shy too, you can text me. I don't guarantee a fast reply, but I'll reply before today ends. Please, is there any question? In the absence of questions, let's call it a day. Bye bye. God willing, tomorrow we may be doing control. We're doing analog system. Yeah, that the telecom course. So bye bye. God be with us. Please, I'm waiting for you all to leave.